Hello there. So in this presentation, we're gonna finally see the existing theorem for the heat equation. This is like this is the top of a mountain. Okay, so finally we're gonna get somewhere. That's we had working all this month to get here. So this is we have been working to really understand as mathematicians this statement. So let's see how it goes. So theorem system of the heat equation. Okay, so I'm not gonna write it again. So it says if f of x is bounded and integrable, the series we considered last time, that was uxt equals sum n equals 1 to infinity kn e to, in this case I'm gonna put this c because it's no problem to carry this c over here. I'm gonna show you in a second what is this c of sine lambda sub n x, and we know the lambda sub n is n it's n pi over lambda, right? So if f of x is bounded and integrable, the series uxt is a solution of to the heat equation. Let's call it ut equals cuxx for t bigger than 0 and x in the interval 0 L. Okay, with initial conditions u0t equals ult equals 0 for t bigger or equal than 0. Okay, so let's call this guy 1 1, call this guy 1 2. Okay, if in addition oh jeez, what did I do? No, make it, sorry, I think I changed it. Okay, if in addition f has a continuous second derivative and f of 0 equals f of L equals 0, then then uxt from a star, so let's call this guy star. Okay, then uxt from a star or define, yeah, define uxt define in a star, so uxt define in a star, so this guy, right, is uniformly convergent and continuous for t bigger or equal than 0 and well, x in the interval and also satisfies 1.3 that is ux0 equals f of x for x in the interval 0. So let's see what is important here. So some a couple of comments on this. Okay, so let's go back to what we had done. So first of all, we are solving the heat equation with these three conditions, right? And I already have explained that we have a wire between 0 and L. We have an initial distribution f of x that is this guy. Let's say f of x goes like this because I'm lighting a candle, right? Right. So it's very hot here, and then it's not that hot on the borders. But it's important to notice these two guys. These two guys are saying that on the corners is isolated or is cold. It's 0. The temperature is 0. Okay. And now it's really important. Notice this. This is really important. This is the experiment. This is the experiment. Okay. So ux0 equals f of x is this experiment. Now, what is the mathematical model? This is the mathematical model. Okay. So what we are saying is that when t equals 0, this is the initial distribution. Now, for t bigger than 0, you turn off the candle. And now, this is, you don't know what is going to happen, but you trust this equation. This equation is saying that for t bigger than 0, so this is t0, so when t starts running, you have a new dimension. Okay, and it's saying that this temperature is gonna cool down. Okay, so this temperature is cooling down. Okay, so it's like you imagine your wire in the future. So your wire is over here, and the wire is not as red as before. The redness is distributed. Here it was really red here, but now the redness is distributed. Okay. So the question is, what is a good f? Okay, how has to be my initial distribution for this in order to solve this equation? So this is the answer of the theorem. The theorem is saying that f has to be bounded, okay, and integrable. Okay. Oh, I think I'm missing something here. Okay, and also, so f is bounded and integrable. So that's easy because bounded and integrable is in 0L This is bounded and integrable, okay? But this is also bounded and integrable. Could be discontinuous. Bounded means f of x is less or equal than some constant, okay? So that's bounded. For example, this function is not bounded. For example, tangent of x between minus pi halves and pi halves is not bounded because you can find in minus pi halves to pi halves you cannot find an m such that all tangent of uh, uh, all tangent of x is less than a constant. Okay, so that's not bounded. Okay, so we need to be bounded and integrable. Integrable means is continuous or piecewise continuous. So that's fine. So that's we can do Fourier series with that. So that's not too much to ask. Okay. But there is more. If in addition f of x has a continuous derivative, has a continuous second derivative, and f of 0 equals fl. So we have one, 2, 3, and 4 properties for f. So f must be bounded and integrable. F must have a continuous second derivative. So that means you can find the second derivative of f and is continuous. For example, what are not good f? This is not a good f. This is not a good f because that, at least for this theorem, the first you cannot find the first derivative. If you find the derivative of this is gonna be minus 1 and 1. So it's gonna be minus 1 and 1. So this is f prime of this f. If this is f, f prime will look something like this. So this is continuous. So the second derivative, I cannot find the second derivative of this. Okay? It will be, the second derivative will be discontinuous. So the second derivative must be continuous. And f of 0 has to be equals, f of 0 and f of l has to be 0. Okay. So at least for this theorem, those are the conditions we have. Okay. And we will see. So there might be other theorems, but then the proof is totally different. Okay. So this is what we're gonna do. Okay. So here we go, proof. So this is the proof. So we're gonna do, so what is the statement? What is this saying? So is then that's the statement, right? The statement starts here. Then, so I have all these hypotheses. Now then, UXT defining is uniformly convergent, and continuous for t bigger than 0. Sorry, no, that's not the first. That's not the first statement of the theorem. The first statement says that if f is bounded and integral, the series is a solution of this. So this is the first statement. It's saying that this series is a solution of 1, 1 and 1, 2. That's the first thing we need to check. Next, second part is saying, part 2, if in addition f has a continuous second order derivative, then ux is uniformly convergent and continuous for t positive, and also satisfies ux0 equals f of x. So it's saying uxt satisfies 1, 1 and 1, 2 is the first part, and then part 2, ux0 equals f of x. And between 1 and 2, we get the whole, this model, okay? That's the model, okay? Okay, so proof. We're going to start with part 1. Proof of part 1, okay? So, to prove that uxt is a solution of this guy, notice I just put my c, but that c is not a problem, because when I did my separation of variable here, when I did my separation of variables, I could put c here, I could put c here, and then when I do separation of variables, I'm gonna get the c here, okay? And then I just carry that c with t, and then that c is gonna be, as you see, that c is not a good choice because I put custom here. Let's call it a. So let's call it a. If I call it a, this is a, and then if I call it a, this is a, and then so I will have a here, and so on. So you just carry your a, right? You carry your a in all these things, and then what you will get is that a is over here. So instead of c, let's call it a. A, and I'm gonna call it a. Okay. So that will be, yeah, and that's the diffusion constant. Okay, because that a will tell you, depends of the material that you have. Okay, so some are better conductors than others. Okay, it's not, it's just to be more useful when you are using this in chemistry. It's not really a big deal. Okay, so part one says, sorry, let me stop this. Okay, so let's start with part 1. So what I need to prove is that uxt satisfies 1, 1 and 1, 2. So let's check 1, 2. So part 1, let's check 1, 2. So let's start with the easy. If I put ux0, then I get the sum of n equals 1 to infinity, k to the n, e to the minus, no, sorry, is not ux0, is u0t, sorry, u0t. So k to the n is e to the minus a whatever, but then sine n pi 0 over L. So of course this gives you 0, right? Because sine of n sine of 0 is gonna be 0. Lambda n squared t, right? So that's, and then ULT, same thing, sum of n equals 1 to infinity kn, and then here gives you e to the minus a lambda n squared t sine n pi lambda over L, the L over L, and this cancel sign of n pi is 0 for any n. So those two are okay. So check. So this satisfies the borders. Okay. Now I need to verify that uxt is this. Then ut equals a times uxx. Okay. We already did this calculation before. Okay. So since I did the calculations without a's, okay, so let's eliminate the a. So you can just say a equals 1, right? So you can do a equals 1, it's not a problem. So let's make this a equals 1. So my calculation, when I go to my calculations, you're not gonna worry about that. A equals 1, but it's no problem, okay? So when we were discussing in my other video, we were discussing that we need to interchange, right? So it was here, right? So we did derivative of these guys is the same, and I was talking about interchanging, and then here we're talking about term by term differentiation. So I need, if I can switch derivative with respect to time with the sum, this is true. So I'm not going to do it again. I will already do it. Derivative of u with respect to time gives me this one, and then derivative of u with respect to x gives me this one. Okay. So as long as I can interchange derivatives. Okay. So when can I interchange derivatives? With this infinite sum. So we have a proposition 3. What is proposition 3 telling me? We discussed this one last time. So it's saying, so you can change, we're gonna use it twice. We're gonna use it for x and for t. So basically you fix x and you work with t, and then you fix t and then you work with x. So you apply this proposition twice. So let's say you wanna work on the derivative with respect to x. Okay. So we had to find this. Let's say we wanna, let's say we want to apply. Let me change the color so it changes. Looks like a discussion. Let's say we want to apply the proposition 3 to uxt but with derivative respect to time, but using, we will use the derivative respect to time first. So what does it mean? We have uxt, right? And uxt is this infinite sum. This is infinite sum of, it could be n equals to 0 or n equals to 1. In this case, it's n equals to 1, infinity k kn e to the minus lambda n t squared sine n pi x over L. right? Let me see, is that right? And this is with minus. Sorry, this is not lambda squared, lambda n squared t, right? Yeah, e to the minus lambda n squared t sine of n pi. Yeah, okay. Well, let's say here, to be consistent, let's say here lambda n. So lambda n is n pi over L. Okay, so it just it's easy for me to remember that way. Okay, so so what I wanna do is apply the derivative with respect to time. So instead of x, I'm saying time. Okay, so you can just say apply the whole theorem. Instead of x, your variable is t. So that's no problem, right? You just make a mental note and then change this t, right? So that's not a problem. Okay, you apply it to time or to x. So we're gonna apply it here, right? But then we need to move it to this side. So that's what I'm gonna do. So if we can do that, just take time. So that's what we did in my previous video. We verified that when you interchange the derivative of u with respect to time, you obtain this value, and when you interchange it twice with respect to x, you obtain this value. So we need to verify this. So we need to check first. G sub nt is continuously differentiable on an interval. Okay, so in my case, Gn sub t, what is Gn sub t? So for clarity, let me put it here. So this is the derivative with respect to t. This guy is Gn of t. Okay. Just this guy is a constant because I don't really care about that guy because my variable I'm fixing x, so it's a constant. So my G sub n is only about depending on time. Okay. So that's my Gn of t. So first, GNT is continuously differentiable on interval. In my case, is 0L. Yes, that's true. This is exponential, so this is definitely differentiable. What do I need? I need to be continuously differentiable. Yes, I can differentiate with respect to time, and that function is still continuous, right? So let me write it here. So Gn of t equals Kn e to the minus lambda squared nt sine lambda n x. Okay, and g prime. Oh, okay, so that's the first part. So condition 1 for proposition 3 says that Gn is continuously differentiable on an interval I. Yes, Gn, this is Gn, is continuously differentiable on 0L. Check. Okay, next. And assume that this sum is convergent at some point in the interval. Okay, so we need to this sum is convergent at some point on the interval. So that's something we need to check. Find a point when this is convergent, some point in the interval. So well, yeah, but that could be easy, right? So I can just plug in. If I plug in at 0, Gn of 0, the sum of Gn of 0 oh t0 sine lambda n. I need to put, yeah, okay, so we will do this together with another case. Okay, so let's, yeah, that one is probably, we need to check it. So we need to find a point and see that this sum is less than infinity for some point. Okay, and then you will have to check that the sum from 0 to infinity of the derivatives, so you have to check 1, you have to check 2, you need to find a such that sum of g and a from infinity is less than infinity. Okay, it doesn't matter n equals 0 or n equals 1. Okay, that's not. So your gn is this one, no? So you need to find when this series is gonna be converging at some point. Okay, and part 3, we need to prove that this sum is uniformly convergent. So the sum of the derivatives of gn prime of t, that is what? Sum of derivatives, it's gonna be the derivative of this is minus lambda n squared kn e to the minus lambda n squared t sine lambda n x. So you need to prove that this is gonna be uniformly convergent. Is uniformly convergent. Okay, so those are the two things we'll have to do if we want to interchange the derivative with respect to time with the sum. But guess what? That's gonna be homework for you, because I'm gonna do. So we have to do actually 3. Okay. So that will be the first one we have to do. But of course, we're not gonna do all of them because all of them are pretty similar. So let's say this is A. Then we'll have to do B. We have to do same steps for B. Interchange derivative with respect to x of u. So we want to do derivative with respect to x of the sum of these guys of kn e to the minus lambda nt sine lambda n x. In this case, n equals 1 to infinity. In this case, this is your g sub n x. Okay. So we had to do 1, 2, 3. 1, 2, and 3. But for these guys, k sub n. Okay, so we will have to prove that g sub n x, in this case we consider with respect to x, is continuous differentiable. That's easy. Now we will have to find that gn n for some a is less than infinity. So that one is gonna be easy. So this is check g because x can be 0. If we put gn of s0, if x is 0, we get we want to check proposition 2, right? So if a equals 0, gnx or gn0 equals 0, right? Because you plug in 0 here, so sine of 0 is 0, so this guy is 0. Okay, so yeah, probably I'm gonna leave you this one better for homework. The first derivative with respect to x, so you don't have to worry about finding the right a for time to make it this convergent. I mean, it requires less analysis. So you plug in at 0, then you will get 0. So you get condition number 2. So this is converging for a point in the interval 0L. Now, now we need to prove sum n equals 1 to infinity gn prime of x equals, and then we find the derivative of this guy. So sum of n equals 1 to infinity, and the derivative of this is kn e to the minus lambda nt cosine lambda nx times lambda, right? Lambda n. Okay, so we need you in your homework, you're gonna have to prove that this is uniformly convergent. So you see how hard mathematicians have to work to do this correctly. And finally, part C, that is the one I'm gonna do. We're gonna justify that I can interchange the second derivative with respect to the sum. So the sum of n equals 1 to infinity kn e to the minus lambda nt sine lambda nx lambda n squared, sorry, square, and this is square. Okay. Yeah, so this is a square. So so I had to go over here, so I need to justify that this we can do. Okay, so that's what I'm gonna do right now. Okay, so we need to do we need to check that gnn of x, so gn of x is kn e to the minus lambda n squared t sine lambda nx. Okay, so part 1 of proposition 3 says that gnx must be continuous and continuously differentiable on 0L. Is continuously differentiable on 0L. Okay, that's for x. So for the next one, this is true, right? We have to find a such that gna x is less than infinity. So notice that in my case, gna of a, okay, so gna of a is 0 again. gna okay, hold on, this is prime so we're gonna do, so yeah, so let me put this one here. The one that I want So gn of let me see here. Yeah, so what happens is that I had to apply twice. I had to apply the derivative twice here. So I already applied one derivative. So my other derivative, actually my g of x is gonna be this one. Okay, so my g of x is gonna be this one because I already apply. So I need to apply one derivative at the time, right? So I'm using your homework. So my gn of x is gonna be, this is gonna be my gn of x. Okay, so the derivative with respect to x of this one is gonna be k lambda n. Okay, and okay, sorry guys, I had to find the whole derivative of this, and that's gonna be my gn of x. So because I'm using your homework, I had to use your homework. Okay, so you have to do the first derivative with respect to x, and I will do the second derivative with respect to x, but using the one that you already use. Okay, so gn of x is gonna be, so the first derivative is cosine, so it's gonna be this one. It's gonna be cosine lambda nx, and then times kn k sub n lambda sub n e to the minus lambda n squared t. Okay, because that's my g sub n x is that derivative. Okay, so is continuously differentiable on 0L? Yes, because remember x is moving between 0 and L. T is different. T is all real numbers, but cosine is between 0 and L. Okay, so this is first part, good. Second part, I need to find an A such that gn of A is less than infinity. So again here, for my g on n, so my sum n equals 1 to infinity, and I'm gonna choose A equals to 0. You know, I hope you're not confusing this A. This is an some letter, right? Some number A in the interval 0L. Okay. Find A. Find A in 0L such that so let me change it, because let me say instead of A, let me change, like, let me call it alpha, because I'm using A over we were using A here, right? So it doesn't have to do with this A, right? I don't want to confuse you. So you have found some alpha in the interval such that this sum is convergent. So we need to find A, and in this case A is 0, and gn of 0 is what? Sum of n equals 1 to infinity, and then kn lambda n e to the minus lambda n squared of t. Okay, so that one that one we need to prove that is less than infinity. Okay. So let's leave it like detail one. So I will make it in another video or assign it like homework, but it's gonna be easy. You will see because I'm gonna do something very similar to this one, so I don't wanna do it twice. So this should be less than infinity. Okay. So we will see how do we prove this. Okay. Now, so the your calculus 2, your rational test, your ratio test should work for this to prove that this uh, is less than infinity. So it's a convergence series. Okay. So we will do it probably in another video or assign it like homework. So part 2 is fine for the proposition. And so I don't want to solve in those details because that's not what important. What is important is the uniformly convergence. So the book skips all this, but I want to go through with you through the proposition so you can do your homework. So for proposition 3, we need to prove that this is uniformly convergent. Okay, so now that's what we're gonna do. So we need to prove so let's put it here in the theorem now. Let's go to the proof of the theorem. So now we skip all that discussion I made. All the discussion is you're supposed to be able to understand it by yourself when you read the book. By the way, I'm following in this part. I'm following the book by Gunther and Lee. They're doing a good job on this section. Gunther and Lee, and this is page 146. But of course, you will see that my proof. You're gonna see that they do really short proof. Okay, so you're gonna have to. But hopefully you'll understand it better since we have done all this work. Okay. So what we wanna do. So we are gonna check. So we check that 1, 2 is fine, right? So in order to prove 1.1, this one, we need to prove that 1.1, oh no, that the the solution we need to prove that for a star we can apply term by term differentiation. Okay. So in order to do this, and this is all the discussion I just did. I just write it down as part of the proof. Okay. In order to complete this, the three series ut ux and uxx más in order to complete this, the three series must satisfy the turn by turn differentiation. So we will only work on the last one, in this one, since the proof is similar for the other two. Okay. So it's in using proposition 3, we need to verify the convergence, the uniform convergence in a region D which contains the fixed point, let's call it x bar t bar. Okay, so what are we doing here? So we want to make sure that this series, the series star, is uniform convergent, right? So how do you do that? So you fix the point, you fix x, and you prove uniform convergence. Well, in general, you fix the point xt, right? So you fix the point xt. So this is x bar, this is t bar, and you want to make sure that the series is convergent, uniformly convergent at this point. Okay. So you fix the point. Okay. And then now you can start working like calculus 2. So that's why you fix the point. Okay. So such a region is, so D is equals to xt, t bigger than t bar over 2, and x is between 0 and L. So we leave x be between 0 and L. So that's the region. And so all these points, xt, t has to be bigger than t halves. So t halves, this is t, so bigger than t halves. So they just want to move away from 0. So this is where we're gonna move. This is the region on the bottom. Okay. This is a technical thing, just so all the calculations are correct, but you might not see it when in the proof. But I had to mention it since just to make sure we can do the analysis correctly. So to check uniform convergence, So to check uniform convergence for the series UXX, the series obtained by differentiating term by term twice with respect to x is the following. So you have u xt, right, and you're gonna find the the second derivative, right? So we differentiate term by term as we had done before. So we got derivative of sine is cosine, derivative of cosine is minus sine, so and lambda n goes twice outside, right? So we will get sine of minus lambda n squared k to the n e to the minus lambda n squared t times sine sine, yes, sine lambda n x. Okay, so that's the series I want to check that is uniform convergent. Okay, because this is an infinite sum. All that I know, this sum could be infinity or not, or not converge to any number. Okay, not infinite sums are not necessarily convergent for numbers. Okay, for example, sum of 1 over n is infinity, or at least it's divergent. Okay, it's divergent, but it's really infinity. So imagine how can I prove that this interval, that series is less than infinity for all t bigger than 0, or at least for all t bigger than t halves. Well, in this case, I'm fixing in my t, right? So t t bigger than t halves and x between 0 and L. Okay, so that's what I have to prove, that this series is well defined on this, on the bottom, this bottom. Okay. But since I fixed in a point, I'm going to start working with basically calculus 2. So at the beginning, we assume that the initial temperature distribution is bounded and integrable. So recall, we assume that the initial temperature distribution f of x is bounded and integrable on x in 0L and f of x less or equal than m. Okay, so f is bounded and f is also integrable. So we said that over here. Remember I said f here. F is bounded at integral 1 and 2. Okay. Because f is bounded and integrable, then the actual value of the k-ends, remember that the k-ends are given by 2 over L integral between 0 and L f of x sine lambda sub n of x dx. Okay, so since this integrable, so k sub n is this, so the actual value of this is like that, right? But then this is less or equal, and this is a property of integrals. I don't know if you remember this one, but let's put it here. The actual value of the integral of f dx is less or equal to the integral of the actual value of f dx. Yes, this is, we write it down in calculus 1. You might not remember, but we did. So this is 2 over L. I always do. So 0L, and then actual value of x sine lambda sub n x dx, right? So basically the actual value go inside. But what is the actual value sine of sine? So the actual value of sine is always less than 1, right? Because sine goes like this. Sine goes like this. So the actual value is always less than 1. So this is less or equal to 2 over L integral between 0 and L f of x dx, because this is the actual value is the same as the multiplication of the actual values, and this guy is less than 1. So there we go. But now by hypothesis, f of x is less than m, so I can write this is less or equal to 2 over L integral 0 L m dx, right? Now I find the antiderivative. This is mx, and when I evaluate, I get 2 over L, and then you do x between, well, mx, right? Mx between 0 and L. So finally you got 2L m times L. These two cancel, so this is, in conclusion, less or equal than 2m. In conclusion, right? So k sub n, conclusion, k sub n is less or equal to 2m. And let's consider our series. So if we consider our series, we're going to take actual value of that series. So let's say, on the other hand, just to you understand, I'm going to take the actual value of the whole thing here. So I'm going to take the value of this sum. This sum, n equals 1 to infinity, I think it was minus lambda n squared, right? E to the minus lambda n squared t sine n pi x over L. Right? This is my, oh, and I forgot the k sub n, right? Lambda n squared k sub n. K sub n. Okay? So by triangle inequality, so let me put these guys in some orange, because those are kind of, we're kind of reviewing calculus or analysis. You know, calculus and analysis is the same thing. It's just that we never prove those kind of things. So in analysis, you prove those those things. So you're supposed to prove in this in calculus, in analysis, sorry. So this is one property, and for analysis. Another property is that this is the triangle inequality, right? So this is less or equal. You interchange. Remember, you have this in calculus, right? X plus y is less or equal than actual value of x plus actual value of y. So that's something here we're gonna use. So you don't believe me? Just prove it by induction. So this is gonna be sun n equals 1 to infinity minus lambda n squared k n e to the minus lambda n squared sine n pi x over L absolute value. Okay. Now, again, the absolute value of a product is the product of the absolute value. So I can do this absolute value and absolute value product, right? And now this guy, sine n pi x lambda, is less or equal than 1, right? Sine is always less or equal than 1. At least I'm multiplying outside for something, but that sign doesn't have any multiplication or anything. So this is less or equal that sine n equals 1 to infinity minus lambda n squared k sub n e to the minus lambda n t. And now I just prove that my k students are less or equal than 2m, right? So I can also split my absolute value. Let's split it with k student like that, right? So this is less or equal that sine n equals 1 to infinity. The actual value of k sub n is less than 2m, so I'm gonna put 2m. And the actual value minus lambda n squared is just lambda n squared, right? And e to the minus lambda n sub n t, that's always positive, so it's e to the minus lambda n t. Okay. But notice something here we had done here. We have 2m lambda n squared e to. Notice that you might wonder, why did he start doing this this region? We haven't used this region yet, right? So now we're gonna use it. I fix my region to make this trick official. If t is bigger than t half t bar over 2, right? So this is a decreasing function. So t is bigger or equal than t bar over 2. Because I chose it like that. Look at this. T is bigger than t bar over 2. Therefore, this is less or equal that sine n equals 1 to infinity 2m lambda n squared, and this is a decreasing function. That means if t is bigger than that, then this is less or equal than e to the minus lambda n t bar over 2. And this t is fixed. Remember, t bar is fixed. Okay, so that's something very nice. So if this is from your calculus again, if this is, since this one is decreasing, e to the, let's just say like this, e to the minus t is less or equal to e to the minus t bar divided by 2, because it's decreasing. Okay, so the lambda n doesn't matter. So this is by decreasing function. That's calculus again. Okay, so you see, all that we're really doing is applying calculus. We're just we learn some definitions, but we're really just doing calculus 2. That's why calculus 2 is so important. So you have this, and uh, uh, so we have proof. So what do we have proof? We have proof that let observation. Let's observe. So okay, so let's say we want to use Weierstrass m-test because we want to prove uniform convergence of this series. We want to prove uniform convergence of this series, and uh, here I think I told you that the only way, or the best way to, not the only way, the best way to prove uniform convergence is using the Weierstrass m-test right here. So we need to get, let's say we want to prove that the sum of GNX is uniformly convergent. So we need to make this less or equal that m sub n and prove that that series is convergent. Okay. So how do we do this? So that's what we're doing, right? G sub n x is the one that we started using, and n sub n is the one. So let me put it like here. So we want to use Weierstrass m-test with GNX in this case is this one, minus lambda n squared k sub n e to the minus lambda n squared t sine m pi x over L. That's the right one, right? Yeah. So this is GNX, right? And what is m sub n? M sub n is this guy that we just found. 2m lambda n squared e to the minus lambda n t bar over 2. Okay, so in general, you can forget about the sum. So I make this, try to give you what I was getting ux, but if you want, you can forget about this uxx and just consider this term. So you can consider this term. So let's say this is g sub n of x, actual value. Okay. Now, so this is in this case this is equal. In this case this is equal. Okay. And then this is less or equal than this guy, and then this is less or equal than this guy, and then this is less or equal than this guy, and this is my m sub n. So g sub n of x is less or equal than this m sub n. Okay. Now it's easy to prove that the sum of n sub n is less than infinity. So the sum n equals 1 to infinity of sum n equals 1 to infinity 2m lambda n squared e to the 1 minus lambda n squared, right? E to the minus lambda n squared t bar divided by 2 is less than infinity. So that's probably an exercise. So I'm gonna decide which one of these are gonna be exercises for homework. Okay, but this is just using ratio test. So now easy to prove that using ratio test. Ratio test. Sorry for my bad pronunciation. Oh, you see, this theorem is so long that my pen now is, the battery is getting affected. Sorry, let me fix it here. So using ratio test, this is true, right? And the Weierstrass M test guarantees the uniform convergence. Of let's call it star star. In D, in this region D, but you know, you need to prove that this is uniform convergence in x bar t bar, so you just choose D and you prove that it's uniformly convergent. Okay, so you can do it for any t as long as t is positive. So entirely similar reasoning applies to the other series. Applies to the other series for derivative with respect to time, derivative with respect to x. Consequently, we call it star. Consequently, star, this one. Consequently, ut, ux, and uxx satisfies term by term differentiation, and star is a solution or satisfies the heat equation. Satisfies the heat equation how do we call it? We call it 1 1 1 2. So we still have 1 3. Okay, 1 1 and 1, 2. Okay, I think I'm, wow, my goodness, 1 hour 20 minutes. I don't want to lose this video, so let me, I'm sorry it was too long. I think I tried to explain too much. But what we had done is basically simple. We just justify that we can interchange the derivative with the sum. So if we are basically proof that we only did it for this one. We prove that the expression for this is uniformly convergent, uh, and similarly you could do this one and this one. Okay. So with all those being uniformly convergent, then you can prove that you can interchange. And when you can interchange, that's what I show as a motivation over here. Once you show that you can interchange, you can verify that this infinite sum is a solution for the heat equation. Okay, so that's all that we have done. Okay, so I think it's a good experience for you to be exposed to all this analysis, useful for something. Okay, sometimes you see analysis and you have no idea what are you having this kind of experience, and if you like it, that's great. I mean, I always like analysis. But if you don't like it, it's like hard to find a motivation. So I'm trying to give you a real motivation, real physical motivation to like analysis. So that's what we had done. We had done really important. That's something like I could promise you that hardly any engineer can understand this proof. So I will encourage you to use the background in mathematics to force yourself to understand this. Ask me questions, but it's basically we have done basically calculus too. With little trickies. But so in my I don't want to make this video any longer, so I'm gonna do in another video. We're gonna finish with the part 2 of the proof. We just did part 1, okay?